Bismillahirrahmanirrahim. We continue our discussion on deadlock and discuss further more topics in Deadlock chapter. But before proceeding ahead, we need to have a recap of the points or the topics that we have discussed in the previous lecture. In previous lecture, we tried to develop an understanding with the term deadlock and how it is a problem. We define deadlock as a situation in which two or more than two processes are stuck. They are stuck on resources. Every process is holding a resource and waiting for the resource held by the other process. So no process is going to release the resource and are waiting that other process should release their resource so that they can acquire them and continue their functioning. But since no process is willing to release the resource, so they stuck in a deadlock. Then in previous lecture, we tried to develop system model, how we can use symbols, different symbols to draw deadlock if it appears in our system. So in today's discussion, we are going to draw different diagrams, and some of them have been drawn in previous lecture as well. The major components used to represent different activities or different elements when they stuck in deadlock are, for example, we represent the process with circles, we represented resources with squares, and if there are more than one resource, if there are more than one instance of a single resource, so then multiple small either circles or squares are drawn within the big square, or you can also use rectangle for it. Then we use or try to define different factors that bring deadlock in the system. So 4 common factors or 4 characteristics of deadlock are there which need to appear simultaneously. That is no preemption, mutual exclusion, hold and wait, and the 4th criteria is circular wait. So these 4 factors should be present simultaneously in your system in order for the deadlock to happen. Otherwise, the situation will be a live lock, temporary lock, which is then removed on its own, or operating system can handle live locks easily. But deadlocks should be properly treated. So these were the points that we discussed in the previous lecture. Now let's move ahead for today's discussion. In today's discussion, we are going to discuss how we can handle deadlock. So there are some methods for managing or handling deadlocks if they appear in your system. Deadlock is a rarely appeared situation. Generally, live locks appear quite often, and operating system manage them very easily. Even users do not feel that some lock has been appeared. But deadlock is a situation when you feel your system is now jammed. So you try to make it or try to wake up the system, either restarting it or shutting it down forcefully. So some methods are there. If deadlock happens in the system, these methods are applied. We'll be discussing these 3 methods one by one in detail. The methods are, we can prevent the deadlock. The first method, deadlock prevention. How we can prevent the deadlock, that it may never appear in the system. So techniques for deadlock prevention will be discussed. Next method for handling deadlock is deadlock avoidance. How we can avoid deadlock. Since deadlock is a problem and some operating systems try to avoid this issue, but this issue may happen, though rarely, but it may happen. So how we can avoid that this situation must not appear in our system? So we'll be discussing deadlock avoidance method. Then we have to use some detection technique. How we can detect if deadlock is going to happen in our system or not. So deadlock detection techniques will be then discussed next. At the end, once we have detected the system has indulged in deadlock or the system is going to get locked in a deadlock situation, then we have to wake our system up. So for that, we need to have some mechanism for our system to get recovered from deadlock. So some techniques for to get your system recovered from deadlock will be discussed. Recovery from deadlock is possible and how, but at the expense of what? We'll be discussing those factors when we will be discussing how we can recover from deadlock. So let's proceed with today's discussion and discuss what are the methods for handling deadlock. All the three methods will be discussed in detail in today's discussion. Before moving to deadlock handling techniques, some basic facts I want to explain. This slide is in connection to the previous lecture. So some facts when we were discussing about the circular weight in previous lecture. So this is in connection to that particular lecture. Some facts about the circles. Keeping in view the resource allocation graph, you need to keep some basic facts in order to detect a deadlock in the graph. Now, what are those basic facts? If the resource allocation graph doesn't have any cycle, if your resource allocation graph does not have any cycle, so that means there will be no deadlock in it. But if there exists a cycle or a circle, then we'll have to look for the deadlock breakers. So if you find a graph or a cycle, if you find a circle or a cycle in your graph, so these are the two possible situations. You now have to look for the deadlock breakers. If there is a cycle, there is a possibility of deadlock. Keep in mind. So cycle brings possibility, but it may not bring the surety that deadlock will happen. So if there is a cycle, what things you should keep in mind? If only single instance of all the resources are there, so if all the resources are having single instances and you find a cycle or circle in resource allocation graph, then it is a must deadlock situation. But if more than one instances of resources are there, if you see more than one instances of resources in your resource allocation graph, then there can be a possibility of deadlock. Deadlock may happen or it may not happen. So here you need to look out for the deadlock breakers. More than one instances may serve as deadlock breakers. So these deadlock breakers then will take the situation more towards live lock, which is generally a temporary lock, and it gets removed with the passage of time, or operating system can handle them very easily. So this slide is in connection to the previous lecture in which we were discussing the resource allocation graphs and how circles or cycles in the resource allocation graph can signify if there is a deadlock in the system or there is a live lock in the system. Now let's move towards different methods for handling deadlock. We have two choices. Either we never allow the system to enter in deadlock situation, the way some of the operating system do, and they ignore this problem, such as Unix. So this is one of the technique, or you can say it is deadlock avoidance technique used by Unix. Either you ignore the problem, that it will never happen. The main reason for ignoring this problem is that such operating systems are claimed to be more secure. So due to tight security, there is no mechanism to handle deadlocks. That's why they ignore this problem, as they expect deadlocks will never happen due to foolproof security measures. But this is not the case with all of the operating systems. So deadlocks do occur, and those operating systems then provide some means or mechanisms or methods to handle deadlock and get recovered from this problem. We are now discussing all those mechanisms one by one. The first mechanism for handling deadlock is deadlock prevention. Deadlock prevention says to prevent the deadlock from occurring, as you must have heard a famous proverb, prevention is better than cure. How prevention is applied? So, prevention says that one of the four necessary conditions or characteristics of deadlock needs to be eliminated. If one of the conditions is removed, so deadlock will never happen. If you remember in previous discussion, we said all of the four necessary conditions for deadlock need to occur simultaneously. If one, two, or three of the conditions are happening, but the fourth one is not happening, still your system is safe from deadlock. All of the four necessary characteristics, factors, or conditions of deadlock need to occur simultaneously for the deadlock to appear in your system. So the deadlock prevention mainly targets these four factors. This technique tries to overcome one of the factors of deadlock. If it hits one of the factors is removed from the system. Still, other three are appeared, or other three have already occurred, but one have been removed. So still your system is out of deadlock. So what were the four conditions? Mutual exclusion, hold and wait, no preemption, and circular wait. If you remember, these were the four necessary deadlock characteristics. All of these four characteristics, all of these four factors should appear simultaneously for the deadlock to appear in your system. Now, how we can eliminate these conditions or any one of them? Here's the mechanism. The first condition is mutual exclusion. Mutual exclusion says, as we discussed in the previous lecture, that one resource should be used by single process at a time. In previous chapter, when we were discussing process synchronization, we discussed mutual exclusion as a beneficial phenomena. But now, due to it, deadlock is getting occurred in our system. So how can we prevent mutual exclusion, since it also brings benefits along? So, as mutual exclusion cannot be prevented completely, since this would make the resource or the data inconsistent. So what we can do? Now we can differentiate among resources by categorizing them in two categories. Some resources are shareable and some resources are non-shareable. So we categorize resources. Two types of resources are there. Some can be shared between different processes and some are non-shareable, that has to be used by one process at a time. Shareable resources are those which can be accessed by more than one processes at a time, and this will not happen, or this will not bring inconsistency of the data or hardware, such as the internet bandwidth. More than one applications are sharing the same bandwidth, and they are not resulting in inconsistency of this resource. So the internet bandwidth is a resource shared by more than one process at the same time. It is a shareable resource. You can run more than one applications at a time on your internet bandwidth and it will work correctly. So it is a type of shareable resource. While the non-shareable resources are those which must be accessed one after another, but not simultaneously or concurrently, as simultaneous access to non-shareable resource will bring inconsistency, such as printers and other input-output devices. More than one application cannot access printer at the same time, as printing has to be proceeded for one process at the time. So mutual exclusions need to be applied only on the non-shareable resources and not on the shareable resources. By doing this, we can prevent mutual exclusion or limit it to some extent, but it is not completely removed. The second condition is hold and wait. Hold and wait say a process is holding a resource and waiting for another resource to be assigned to it. How this condition can be prevented? Operating system need to ensure that any process that requests some resource must not hold any other resource. So, operating system need to ensure that whenever a process requests some resource, it does not hold any other resource. How this can be ensured? Two options are there. These are the two options. The first, either process requests all its required resources before it starts execution, and if all the resources, all the requested resources are available, they are then assigned to it. While the second option is operating system can allow a process to request a resource only when it is not holding any other resource. So in this way, hold and wait condition can be prevented. So two conditions are written, two options are written here to prevent hold and wait. Require resources require process to request all the resources in advance before it starts its execution, and if those resources are available, operating system need to allocate them to that particular process. So this happens before the process execution. Well, the second option is that allow the process to request a resource only when the process has none. That means it has to request a process one by one. But by doing so, some of the resources may be underutilized and resource starvation may be the result. So low resource utilization may happen, which can bring starvation, as some of the resources may never be or very rarely be requested. Third condition is no preemption. No preemption states no resource can be taken away from a process forcefully or without its consent. Now, how this can be prevented? If a process requests a resource which is not currently available, so it has to voluntarily release all its held resources, since it cannot proceed ahead, and deadlock may occur due to that process. The released resources are added to the pool of resources and made available for the other processes. So, how we can prevent no prevention condition? If a process that is already holding some resource goes to request some other resources which are not available at the time of its request, so that process need to release all its held resources. The preempted resources are then added to the list of resources for which other processes are waiting. So that particular process who has released all its resources then will have to be restarted and will request all its resources again in order to complete its execution. The fourth condition is circular wait, which is very common, and we generally target the circular wait when we draw the resource allocation graphs. Circular wait can be prevented by assigning numbers to resources. So processes are allowed to request resources in increasing order of their numbering and cannot request in decreasing order. For example, a process holding a resource number R5, let me write it. A process is holding a resource number 5. Now, once we have numbered the resources, so it can request resource higher than 5. For example, it can request resource 6, 7, 8, and so on. But it cannot request resources lower than 5. It cannot request resources less than 5. So resource number 4, 3, 2, 1 cannot be requested by this particular process. So if you find a situation in which you find a circle that a process, for example, let me clear this up. If you find a situation that process 1 is holding a resource R5, process 1 is requesting for resource R5. R5 is assigned to process P2. Now, P2 cannot access resource lower than R5. That means it can access or it can request resources higher than 5, resource number 5. So if P2 is assigned resource number 5, but P2 is requesting for a resource which is lower than number, for example, it is resource number 4 which is assigned to P1. Now P1 is going in correct order. It is holding resource 4 and requesting resource higher than 4, which is R5. But P2 is the one which is going in reverse order. Since you can see a circle in this case, that means we can remove this P2 from this circle. And ultimately, the resource held by P2, which is R5, will be released. And P1 is requesting for this resource, so it will be assigned to P1. So in this way, we can remove circular wait. You can number the resources, and processes can request the resource only in higher numbers. They cannot request resources from the numbers they have already, lower than the numbers they have already acquired. The next mechanism or the next method for handling deadlock is deadlock avoidance. Deadlock avoidance requires some information in advance, and the information is that every process declares its required or maximum demand of resources right from the start of its execution. So, operating system requires some information in advance. What is the information? That every process must declare its maximum demand of resources in advance before it starts execution. Then the deadlock avoidance algorithm examines the resource allocation state to monitor the circular wait which may lead to deadlocks and ensure that circular wait will never occur. So then deadlock avoidance algorithm will be run in order to observe the resource allocation state to find out the circular wait, since circular wait can bring deadlocks. Resource allocation state is defined by the number of available and allocated resources along with the maximum demand of all the processes, as this information will be required for the deadlock avoidance algorithm. So how you can define resource allocation state? It is the collection of number of available plus allocated resources plus the maximum demand of all the processes in the set. We need to define safe and unsafe states for the resource allocation. When a process requests a resource, operating system first analyzes if the immediate allocation of the resource to the requesting process will leave the system in safe or unsafe state. So, when a request is received by the operating system has to decide if immediate allocation will leave the system in safe or unsafe state. If it is a safe state, resource is allocated, but if it is unsafe state, the request is then not granted. Safe state can be represented if all the processes are representing safe sequence. All the processes are showing safe sequence. Safe sequence of process is if the resources requested by a process can be satisfied by the available resources as well as resources held by other processes. If immediate request cannot be granted, the process must wait until another process completes its execution and releases the resource. When the resource is available, it is then assigned to the requesting process, which after utilizing would release the resource. And then other processes requesting for the same resource would then avail it. And hence this process continues, and it will not create a deadlock, since no process is waiting for one another. This sequence of processes is known as a safe sequence. Some basic facts need to be kept in mind related to safe state. If the system is in safe state, then there is no deadlock. So you are lucky if your system is in safe state. So there will be no deadlock. But if the system is in unsafe state, where processes do not have safe sequence, so there will be a possibility of deadlock. If your system goes in unsafe state, then there can be a possibility of deadlock. There is no surety that deadlock will happen, but still there is a possibility. Now we have to look for the deadlock breakers. If you remember in the previous lecture, we said you have to look for the deadlock breakers. Now the deadlock avoidance algorithm ensures that system will never enter this unsafe state. You have to run that avoidance algorithm that will ensure that your system will remain in safe state and will never get into the unsafe state. There is a very slight difference or margin in safe and unsafe states. One single process can make system to enter the unsafe state where there is a possibility of deadlock, while safe state or the safe sequence of process is deadlock free. So if your system is in unsafe state, there is a possibility of deadlock. Here you can see I have drawn it in a square. That means in a rectangle, that means there is a possibility. It may happen or it may not happen. But if your system is in safe state, there is no possibility, there is no guarantee of deadlock. Your system is deadlock free if it is in safe state. That is all for now. In today's discussion, we had a talk on different methods for handling deadlock. There are some techniques, there are some methods for managing or handling deadlock, and we are discussing those techniques. The first technique or the first method that we discussed today is deadlock prevention. How we can prevent deadlock to occur in our system. Deadlock prevention targets the 4 necessary conditions of deadlock, which are mutual exclusion, no preemption, hold and wait, and circular wait. Since we had said that all of these 4 necessary conditions or necessary factors must occur simultaneously for a deadlock to happen. If any of the 4 conditions is not happening, still deadlock will never appear in your system. So deadlock prevention method mainly focuses on hitting or removing one of the 4 necessary conditions. Different techniques have been discussed how any of the 4 necessary conditions can be handled. For example, the first condition is mutual exclusion. Mutual exclusion says one process should utilize a resource at a time. So in that case, we categorized the resources. Some are shareable and some are non-shareable. So shareable resources, for shareable resources, you do not need to apply mutual exclusion. But on non-shareable resources, you need to apply the mutual exclusion condition. So in that case, you are limiting the mutual exclusion to some extent. The next condition is, deadlock condition is no preemption. No preemption means you cannot take away the resource from a process by force. So how it can be prevented? So two options are there. Either a process, before its execution is started, it requests all its resources in advance, and if these resources are available, operating system assign them all at once. But if they are not available, the process, then second option is, need to request one resource at a time. It requests one resource, utilize that resource, release it, and then request another resource. In this way, it continues its execution. The third condition was hold and wait. Now, how we can remove hold and wait condition? How we can prevent it? Operating system need to impose a condition on all the processes that they cannot keep on holding resources and request other resources while they are holding some other resources. So there is a sequence. Operating system asks them to request all the resources either advance or request only if they are holding no other resource. So if they are holding some resource and request some other resource which cannot be assigned to it immediately, that means it is not available at the time. So in that case, the requesting process need to preempt all its held resources. It has to go back, get restarted, release all its resources, and then come back again and request all the resources, either all at once or one after another. So in this way, we can prevent hold and wait. Well, the fourth condition is circular wait, in which we said circular wait is very easy to be identified in the resource allocation graph. So how we can prevent circular wait? We can assign numbers to resources, and every process has to request a resource in increasing order of the numbers. So if a process is going to request a resource lower than the resource which it is already holding, that means this problem is going to get stuck in deadlock and create problems for other processes. So that process is then terminated, all its held resources are released, and they are then assigned to other resources if anyone is requesting for that resource. So this is the topic that we discussed. We also started another method, which is deadlock avoidance. Deadlock avoidance mainly looks for the safe state. It tries to keep the system in safe state. Now, what is a safe state? If processes are requesting resources in such a manner that no process is causing trouble for the other process. So in this way, a safe sequence of resources are occurring in your system. So this will make the system in safe state. Until and unless your system is in safe state, there is no deadlock. Once it goes to unsafe state, there is a disturbance between the processes and resource assignment, then there is a possibility of deadlock. We'll continue our discussion on deadlock avoidance and discuss deadlock avoidance algorithm in the coming lecture. I hope today's discussion must be clear to you. I thank you. We'll continue our discussion in the coming lectures on deadlock avoidance. I thank you all.